Hello, you are watching video number 1 for Mr. Sweeney's AP Physics C class on momentum. And in this video we're going to be covering section 6.2 of your notes on momentum and impulse. And I'll start this by talking about momentum. And the momentum is the product of an object's mass multiplied by its velocity. You'll oftentimes hear me talk about the significance of momentum, and I typically refer to momentum as the inertia, or the mass of the object in motion. It's inertia in motion. This idea of momentum is captured by the equation, so you can mathematically model it as momentum, that's a symbol P, equals mass of the object multiplied by the velocity of the object. So momentum equals mass times velocity. When we talk about momentum, the most significant way for us to look at this is this idea of an impulse. Impulse being the change in momentum an object undergoes. The reason why it's significant to look at impulse is because impulse is an active thing that's acting between two objects. So one object pushes on another object, it imparts some impulse on it, and the object will gain some momentum. So when we're trying to impart an impulse, or we're trying to change the momentum of an object, we apply a force to it over a period of time. This will cause the momentum of the object to change. And this allows us to take a look at this relationship between impulse and momentum, and we get what is referred to as the impulse-momentum theorem. And this is the way that this is represented in your AP Physics C notes. It is this is impulse J is equal to the integral of force dt, that is force times time, equals delta P. If force is constant, meaning force is not given as a function, this relationship would just be impulse J equals Ft equals change in P. So the integral of F dt is for non-constant scenarios, where we have Ft would be the constant force scenario. These diagrams here are used to show some of how the impulse-momentum theorem can be used, or how it's applicable in real life. And here I have a scenario where I have a truck, shown in the top left here, that's speeding along with some momentum, mass times velocity. Now this truck is going to come to a stop. In the upper set of pictures, I have this truck, and the truck runs into a haystack. In the lower set of pictures, we have the truck that comes and slams into a brick wall. For the haystack example up top, the change in momentum is an impulse. So there's going to be a certain set amount of impulse that's going to be required to bring this truck to a stop. And if we elongate the time, and this is represented by the haystack, meaning it takes more time for this truck to come to a stop, that minimizes the force. So an increase in time for stopping something would decrease the amount of force that's being applied to it. In the lower example, where you have the object, the truck with the momentum, it's going to hit, say, like a wall of some sort, that's going to cause it to come to a stop very quickly. In this scenario, the time is minimized and the force is a maximum. So the greater time we can cause an object to come to stop, or the greater time over which we change an object's momentum, the less amount of force that we need to apply to it. One of the most realistic applications of this comes into the scenario of personal protective equipment, or safety features. If you think about an airbag that works in the car, the function of the airbag is to increase the amount of time it takes the rider's or the driver's head to come to a stop. By increasing the amount of time it comes to a stop, it decreases the amount of force that would be placed on someone during an accident. The same really goes true for any bit of protective equipment, whether it be a helmet or an elbow pad, a knee pad, something that's padded. The function of those pieces of equipment, in order to keep you safe, is to increase the amount of time that it takes that body part to come to a stop. The increase in the time it takes to come to a stop means a decrease in force being applied to it, and this keeps it safe. Now this applies to almost every bit of protective equipment that we use for ourselves to keep ourselves safe, but also for our equipment. A good example of, say, something protective that doesn't have to do with people would be, say, the rubber casing that you would put over your cell phone. That rubber casing, if you were to drop your cell phone, would increase the amount of time it takes your phone to come to a stop if it was accidentally dropped. This increase in time, though seemingly small, is enough to keep your phone safe so the screen doesn't per se crack if you drop it. So you see this in a lot of different scenarios, from bubble wrap when you put things in packaging, to airbags in cars, to a phone's protective casing. All of them have the same similarity, that they're increasing the amount of time it takes something to come to a stop, thereby decreasing the amount of force being placed on the object. Let's try an example of this, and this is going to be from the calculus point of view. Here we have a 3 kilogram object that's propelled from rest at a time of t equals 0 seconds. So that means starting at initial time, and it has a net force. The net force acting on this is variable, and it's given by F equals 0.25 times. So as the force is being applied to this object, it's growing with time. What I want to know is, what is the velocity or the speed of the object at 5 seconds? So over 5 seconds, this force is acting, giving a variable increasing force to it. I want to know after 5 seconds how fast it's going. To start this off, we're going to take a look at the impulse of this. The idea being, if we could find the impulse that was applied to it from the object starting at 0 velocity, the impulse will determine what its final velocity is. So I'm going to find the impulse, then I'll find the velocity of the object. And we'll look at this as impulse equals the integral of force times dt. And that is impulse equals the integral of our function for force, 0.25t dt. Taking the integral of that gives us impulse equals 0.125 t squared. Now this is showing the impulse at any point in time, but when we're looking at the impulse, we have to find the change in impulse. So the impulse, how much impulse was applied over it, and that's going to be the impulse at 5 seconds minus the impulse that's there at 0 seconds. This is going to give the total amount of impulse, or the change in impulse, that was given over that time period. And of course the 0.125 t times 0 is going to be 0. So we just get really 0.125 multiplied by 5 squared, or 0.125 times 25. That gives us a total impulse applied of 3.125 kilogram meters per second. That is how much change we've gotten in terms of our momentum. Taking that one step further, if that's our change in momentum, I can take a look at change in momentum and say that the impulse is equal to change in momentum, which is the final momentum minus the initial momentum, also equal to the mass times the change in velocity. Plugging in for our values, we have 3.125 kilogram meters per second. That's what our change in momentum is. It starts at 0, it ends at some final velocity, so 3 times final velocity is going to equal 3.125 kilogram meters per second, and that ends up giving us a velocity final of 1.04 meters per second. This is how fast it's going when all is said and done, 1.04 meters per second. There's a couple of graphs we need to be considering in this. And the first graph that I'm going to speak about is the momentum as a function of time graph. So this is showing how much momentum an object has as a function of time. And the significant thing here is that the slope of the momentum as a function of time graph, that is the force applied at that time. So to change the momentum, you need to be applying a force over a period of time. But the change in force over the change in time, that is our change in momentum. And we have this equation, and you see this in your reference tables. It says that force equals change in momentum over change in time, or force equals dp dt. Looking at the graph on the right, if you ever presented a graph of momentum as a function of time, the slope of the line, which is equal to the change in y value over the change in x value at any point in this graph, would always give you the force at that point. So the tangent line at any point on this graph, that is equal to the force applied to this object at that time period. Let's try an example where we look at this idea where force is dp dt. The momentum of a moving object as a function of time is given by the expression momentum equals kt squared where K is a constant. I want to know the force causing this motion as an expression. So I want to, instead of giving this expression in terms of momentum, I want to give this expression in terms of force. So I take a look at my concept. It's force equals dp dt. And I want to apply the derivative with respect to time to the function that's appropriate for momentum, and that's kt squared. And the 2 would drop down, and we would end up with a force equal to 2kt. And that is the function for the force applied to time for the function that gave us momentum. It's just a derivative of the momentum function is the force function. Finally, there's one more graph we want to take a look at, and this is the force as a function of time graph. So if we're given how much force we have as a function of time, we could figure out that the area under the force as a function of time graph, that is equal to the impulse imparted over that time period. So force times time, or force as a function of time, they both give us the change in momentum over that time period. And this is that equation that we started with earlier when we did the impulse momentum theorem. Impulse equals the integral of force times time. So there's two graphs we need to be concerned with here. Momentum as a function of time, where the slope of that is going to be the force. And then we have force as a function of time, where the area under the curve is going to be equivalent to the momentum. That wraps it up for this set of notes on impulse and momentum.